sides, and you have lambda equals A. If somebody gives you a polynomial that's second order, I've never derived this, but I did have to memorize it in high school. There's the quadratic equation. And because it has a square root in it, it gives you two answers, which is what you need from the fundamental theorem of algebra. This will have two roots in the complex numbers. If somebody gives you a third order polynomial, again, in the unknown lambda, there's a formula that I hope no one here has ever memorized. You have, like, I don't know. Anyway, it's long, but it just involves square roots and cube roots and these coefficients here. If you have a fourth order polynomial, again, it's an even longer expression involving the same arithmetic operations. And if you have a fifth order polynomial, there's no solution in terms of radicals, but there are special function solutions like ring radicals or hypergeometric functions. And sixth order and seventh order and so on. And the important thing about all these functions, they're perfectly well-behaved complex analytic functions. And they return to you, they are, for an nth order polynomial, the solution is an n-valued function, because of course it has to return to you n roots. This is something that's guaranteed for polynomials. Okay, and you can keep going sort of as far as you want. So what I promised you is that as you work your way down this list, there's a dramatic transition with important physical consequences. And I would forgive you if you thought that this was the transition here. It's a very important and interesting bit of mathematics that, beyond fourth order, there are no solutions in terms of radicals. But I can't think of a single physical consequence of this. Like if I take 5 coupled oscillators and measure their resonance frequencies, they're not dramatically different than 4. Okay. If you're a real big fan of getting in the weeds with solutions to polynomials, you may know that between 7th and 8th, there's some interesting consequences for one of Hilbert's open problems, the 13th problem. That's also a wonderful bit of mathematics. As far as I know, no physical consequences. The transition that I'm going to talk about is probably not obvious from looking at these functions, but it happens right here. When you go from second order polynomials to third order polynomials, their solutions have really interesting and rich topology that just involves knots and braids, and not in any like abstract way where you have to do somersaults to see these things. Like you just plot these functions, you will see these structures. I should say, like, I'm completely happy to be interrupted. Big question. So the physical consequences, as I sort of alluded before, is that if you're doing just F equals ma, classical mechanics, and you have a system of n coupled oscillators, and you want to find their resonance frequencies, those resonance frequencies are exactly the roots of an nth order polynomial. So what I mean by that is if you have some masses and linear couplings, they could involve linear coupling to displacement, linear coupling to momentum, or if you have 3 of them, or 4 of them, or 5 of them, and you write down F equals ma, it's not hard to turn this into an equation that looks like this, where x is a complex n vector. The real part encodes the positions, and the imaginary part encodes the momenta. I feel like this is just Hamilton's equations. And the time evolution is generated by an n by n matrix here. And so F equals ma very quickly turns into this if all you have are linearly coupled oscillators. And then this matrix is not hard to find. It's just some combination of the springs and dampers and things like that. And it is this matrix's eigenvalues that are the resonance frequencies. Any questions at this point? So if you're a physics 260, 261 student, you haven't learned this yet, but in your next mechanics class you will. So instead of root k over m, you find this and it's all the roots of the polynomial. And again, the eigenvalues of any matrix, how do you find it? You compute the characteristic polynomial, which is easy, and then you find the roots of that polynomial. And what I'm going to tell you is that on this side of the line, there's no topology to be had. On this side, there's something very interesting will happen. So maybe you might have wondered, all this nice math that I'm talking about is really only true. This elegant math is only ours to use if we're letting these coefficients and their roots be arbitrary complex numbers. And there's a lot of very nice math to take advantage of. But is that going to be relevant to physics? Like, why would I ever want a complex valued frequency? So to answer that question, let me give you a very short introduction to the field known as non-Hermitian physics. It's a field that is obsessed with this equation. Like the sort of fanciest restaurant in town, which has no sign out front, this is an equation which is so important it has no name, at least as far as I know. It depends what you think you're doing when you're using it. If you think you're doing quantum mechanics of an n-level closed system, this is the time-dependent Schrodinger equation. If you think you're doing F equals ma with n masses and there's springs and such, this is Newton's equations. And if you're doing circuits with linear elements, it's Kirchhoff's law. And if you're doing any kind of linear wave physics, it's your normal modes. And even if you're doing the quantum mechanics of open systems, this is your Lindblad master equation for the evolution of density. So this equation shows up a lot of places. And basically my point is the following. There are some situations in which you should really assume that this matrix is Hermitian, closed quantum systems. If that's the case, I have nothing to tell you. This talk will be meaningless. But a lot of these other situations, it's very natural for the time evolution to be generated by a non-Hermitian matrix. And I'll explain a little bit of that in a minute. But the point I want to make is that if you have learned about this equation, always assuming this matrix to be Hermitian, there are some gigantic surprises that emerge. Not little qualitative ones, but really big ones. Some of those surprises just have to do with the properties of the matrix itself, like that its eigenvalues will be complex, that its eigenvectors aren't orthogonal, perturbation theory is very different. In addition, beyond just sort of the properties of the matrix, this equation, when it has a non-Hermitian matrix there, has a lot of weird behaviors. Again, if you're used to unitary evolution, there's no adiabatic theorem. You have non-reciprocity, Berry phases and related concepts work out very, very differently. And this is important. The reason that there are a lot of people studying this is that there so many physical systems fall into this category, whether you're working with circuits or optics or acoustics, and whether you're using them to build sensors or to understand band structure, or whatever. There are a million situations where you find yourself thinking about this equation with non-Hermitian matrices. In this talk, I'm going to be focusing on just one of these things, which is that the eigenvalue spectrum of this matrix has some interesting structure to it. I will pretend that there might be enough time at the end of my talk to discuss this, but there won't be. Okay, so what are we talking about when we talk about eigenvalues? We imagine that we have a physical system, let's say 3 linearly coupled objects. Its equation of motion, again, just F equals ma is this. That matrix, if I write it out as 3 by 3 matrix, here it is, perfectly arbitrarily. Now, if the system is really lossless, then this matrix has to be Hermitian. And if you like mechanics, that means if all I have here are masses and springs, or if you like circuits, if all I have here are capacitors and inductors, this matrix has to be Hermitian. But if you live in the real world, where it's impossible to keep other things out. In fact, if you just say, I'm going to allow for any linear coupling here between position and momentum, then it turns out that this matrix is completely unconstrained and can be any matrix of the complex numbers. There's no particular symmetry it has. And if you want to build it out of mechanical things, it will be masses and springs and dampers and a Coriolis type force. Electrically, you have these elements here. And we don't typically build things this way, but these are just tangible representations of all the linear couplings you could imagine.
Also negative this equation.
Yeah, all these things, let's this can certainly have an arbitrary sign, this can have an arbitrary sign. I'm sort of going to assume that these are positive. But nothing, yeah. Why do you ask?
Because it's arbitrary metric.
Yeah, yes. Yeah, in fact, everything that I say would hold even for negative values here. You'd be talking about some weird physics, but yeah, but I'm not going to include any nonlinearity. So if you had negative damping and it rang up, the limit cycle is out of the picture I'm talking about. When I'm talking about would accurately describe the ring up.
Right. So you want some sort of, right.
Yeah, I mean very seriously, just linear system. These are linear couplings, and we'll keep everything in the linear.
Yeah, what is the n-dimensional vector, not 2 n-dimensional?
Because you have 3 positions and 3 momenta.
It looks like 2n. That's why I'm asking.
So you have 3 complex. You form each complex number out of an x and a p. X plus ip is one complex number. The other x plus the other n. These are. I would so much rather not have people be lost. So please do. Okay, so the spectrum of such a thing will be determined by the characteristic polynomial of this matrix, which I've written out here. And these coefficients are some combination of these matrix elements. They're certainly determined by the matrix elements in some complicated way. But once they are, you're sort of all done with this matrix, and you're just trying to find the roots of this polynomial. And so whenever you're changing the resonance frequencies, you are changing these coefficients. If you don't change those coefficients, you're not changing the resonance frequencies. And visualizing how this tuning works is the entire topic of my talk. That's all we're going to be discussing. Okay, so again, the resonance frequencies of n oscillators is given by a polynomial like this, where the coefficients, the n complex coefficients, specify what the polynomial is and hence what the spectrum will be. It's pretty easy to do just one transformation and remove the trace of the matrix. We're never very interested in that, it turns out. And that turns out, the trace turns out to be this coefficient. So we can always drop this one and end up with n-1 complex numbers. So if I think, what is the space of all such things, of all such polynomials? n-1 complex numbers is basically twice that many real numbers. And that is, some kind of Euclidean space, just of a relatively high dimension. And what I mean by the space of all polynomials is that every point in this space, uniquely, its coordinates, if you like, uniquely specify these coefficients. And so they uniquely specify a polynomial. Okay, there it is, a specific polynomial. And when we go to find the roots of this polynomial, it will in general be n points in the complex plane. So I've imagined that this is a fourth order polynomial, and here are its 4 roots. So where's topology going to come from? This is the world's most boring space, just Euclidean space. To see where the topology comes from, let me ask the following. Suppose that I start at this point that I showed you and smoothly change where I am around the loop. By which I mean, let me consider different polynomials whose coefficients are varying around this loop. And if I imagine sort of doing this as a function of quote unquote time, and asking what the spectrum does as a function of this time, one thing I can tell you just from common sense is that whatever the spectrum looked like at the start of this loop, you have to get exactly the same spectrum at the end of the loop. You've literally come back to the same thing. Beyond that, there are some nice theorems that tell you that these roots only change smoothly as you do something like this. And so if my loop is very small and none of my eigenvalues change very much, each might deviate a little bit and then come back to themselves in this fashion. It's sort of a plausible thing that they might do for a very small loop. If I do a slightly different loop, I get slightly different trace over here, but no giant qualitative changes. On the other hand, if I ask for all these things to hold, but I consider doing a much larger loop, such that the eigenvalues go all wandering all over the place in the course of this loop, then they can wander all over the place smoothly and return to themselves while tracing out something like this. Smooth evolution, but the set of points as an unordered set is returned to itself. So this kind of object here is called a braid. And yeah, this is sort of our first insight about interesting topology. If I consider another very, very different loop like this red one here, again, the spectrum is always the same at the start and it's always the same at the end, but the wanderings of each eigenvalue might be very different and might lead to a qualitatively, we would say topologically distinct braid. If you notice, this red braid is very different from this blue braid. So I would say that the first takeaway here is that every loop in control space corresponds to a braid of eigenvalues. There's a correspondence between them. But there is a bit of, there's something puzzling here because like this braid is topologically distinct from this one, which is topologically distinct from this one. But when I go and look at their corresponding loops, these loops can be smoothly deformed into each other. There's no obvious topological distinction between them. So to see what distinguishes these loops in reality, let me use the magic of PowerPoint. This is the slide transition feature to smoothly deform this braid into this braid just by really just pushing stuff around. So if you watch it, here I am just pushing those two braids and it now turns into this. I'll go back and forth a couple of times so you can see what we're doing to transform the rightmost braid into the middle one. And up here, I've shown a notion of what the control loop is doing to go from a control loop that gives you this to a control loop that gives you this. And the important point is that to change the character of a braid, you have to push two strands through each other. That's what changes the braid topology. And if you ask what that is, at the point that they're touching, that means you have two eigenvalues that are exactly equal. You have a degeneracy. So that now provides an answer as to what distinguishes these loops. There has to be a point of degeneracy in between them. So this blue loop is topologically distinct from this red one. There has to be a point here at which the eigenvalues have a double root. On the other hand, a point like this in a high dimensional space is not enough to make a topological distinction. I can for sure deform this blue loop into this red one, avoiding that point. On the other hand, degeneracy is not going to be an isolated point. Degeneracy, the equality of two complex numbers, is a two-dimensional constraint, a single complex constraint. So it's going to be a curve or a surface of 2 dimensions less than the full space. So in my cartoon that looks 3-dimensional, degeneracies have to occupy a 1-dimensional curve. And that is adequate to make topological distinctions between loops.
Well, the degeneracies, different physics giving you the same solutions?
It's just a bunch of masses and springs and dampers. And those parameters have a certain value. And as you change those values, the eigenvalues wander around in space. And if you fine tune them well enough to bump into a point on this orange line, you will get a degeneracy. But they are rare in the sense of being only 1 dimensions out of 3. But yeah, it's the same. It's just my masses and springs, and I'm turning the knobs in those spring constants. And it's just measuring the resonance frequencies.
Does the distance between the base point and the first curve of degeneracies tell you anything? Like how far you have to go away from it?
It told you that I am free to draw this cartoon however I want. Okay, that's going to be my next point.
Oh.
So more precisely, we can say that every loop that doesn't actually bump into these degeneracies corresponds to a topologically, a specific topology of braid. That's the correspondence. So if you have 2 braids that are topologically equivalent in how they avoid these degeneracies, they will give you, sorry, you have 2 loops that are topologically equivalent in how they avoid these degeneracies, they will give you 2 braids that are topologically equivalent. But this is just a cartoon, and it would be nice to have a real picture. So what I mean, in order to set the stage for a real picture, here's the space of all polynomial coefficients. It's just boring old Euclidean space. We know that the degeneracies occupy 2 dimensions less. They have codimension 2. But we don't know like what kind of shape they make. I just drew whatever line PowerPoint gave me. But I know it's going to be 2 dimensions less than the full space. And I'm interested in loops that wrap around those degeneracies. Those are going to give me different kinds of braids. So we're at a good starting point for this because I've already told you that every topologically distinct type of loop gives you a topologically distinct kind of braid. And if you have a catalog of all the loops in a given space, this is a very powerful tool for characterizing that space. This is called its fundamental group. Okay, so what is a fundamental group? Because this will be just sort of one slide introduction. A fundamental group is, you can think of it as just a catalog of all the topologically distinct types of loop in a space. If you live in 3-dimensional space, you're in a boring situation. Every loop in 3-dimensional space can be contracted to a point. So there's only one kind of loop in 3-dimensional space. So we say that its fundamental group is just the trivial group. If you live somewhere a little more interesting, like the surface of a globe, you might think you're in a better position to have fun, but no, it turns out not to be the case. Any circle you draw on the surface of a sphere can also be contracted to. So even though a sphere is different, it's not different as it's regarding its fundamental group. Here's a space with a different fundamental group. It's a plane with a hole in it. What are the topologically distinct loops here? Well, there are loops like the blue one that go around this hole once in the clockwise direction, and there are loops like the red one that go around once in the counterclockwise direction. And any loop that goes around a certain signed integer number of times can be deformed into any other loop that goes around the same number of times. And so it's maybe not surprising that there's a one-to-one correspondence between classes of loops and the integers. We know this is the winding number. You draw me loops in the space, I can tell you what its winding number is around the hole. On the other hand, I keep calling this characterization a group. And the reason that it's a group as opposed to just a set is that if you really want to characterize what kind of holes there are in your space, which is kind of what we're doing, you also need to think about concatenating these loops. So this is the group operation. What happens when I take 2 groups and put them together and call that a new loop? So for example, if I took this blue loop and went around it and then concatenated with the red loop and go around it this way, I have this purple drawing. And my loops are subject to the constraint that their starting and stopping point is fixed, but every other point can be moved around. So I'm free to deform this concatenation until it looks like this. and you can see it has no winding number. Not only does it have no winding number, winding number zero is literally the sum of these two winding numbers. So that's how simple concatenation of loops is in a space like this. There are situations in which it is way more complicated, like a plane with two holes in it, called A and B. Again, you can see that red loop cannot be transformed into blue loop, so there's something going on here. But the more subtle thing is that if I do loop A and then loop B, and get this thing here, or if I do loop B and then loop A, these are not equivalent. I'll leave it as an exercise for you to move things around, but you cannot smoothly deform this loop into this loop, keeping your start and stop point fixed. Okay, so that means that the group operation in this space does not commute, is non-commutative. So we would say that the fundamental group of this space is non-abelian, and that when you stitch loops together, you're not just adding integers, you're doing something much more complicated, something with a much richer kind of algorithm. And the reason that I'm taking you through this is it is exactly this that's going to happen whenever you have more than two oscillators. You're going to find a non-abelian fundamental group for this space. So we have a little bit of a challenge ahead of us, which is the following. In that last slide, I showed you the space and then just asked you to use your intuition to puzzle out what the fundamental group should be. You know, here it's just winding numbers. Here it's sort of a word made out of the letters A and B. That's not where we are. We're in the opposite position. We don't know what our space looks like. We don't know what the degeneracies look like or the space that wraps around them. But we do know its fundamental group. Because I told you a few slides ago that there's a one-to-one correspondence between every distinct type of loop and every distinct kind of braid over that number of strands. Can we work backwards from this knowledge to a nice picture? Nick? Okay, Nick is nodding. I can't. I don't know how to do this. So the only thing I have at my disposal is some brute force calculation. And it's not going to be that. But I'm going to show you this. Okay, so what did the full space, the non-degenerate space within it, and the degenerate space actually look like? I apologize for this notation, but this means the full space. If you have two oscillators, you only have two control parameters. And I'm going to show you that the degeneracy is only a single point. And so the non-degenerate space is the entire plane minus that point. The reason I say that is that this is the most general characteristic polynomial of a traceless 2x2 matrix. The trace gets rid of one of the coefficients. So you tell me what this complex number is, we're done. We've now agreed on what the characteristic polynomial is. So if I regard as an experimentalist, all of the knobs in my lab are real numbers. I don't have so many complex valued switches or anything like that. So let me break this complex number up into two reals. So that's why I say there's a space, two-dimensional space of these things. And then ask where, that's this space. Ask where in this space is there a degeneracy? Well, it's not hard to see that the only way that this equation has two equal roots is when z is 0. So that means your degeneracy is right here, and everything else is non-degenerate. In terms of what we've been talking about, if I now pick a starting point and do a loop, like this red loop here, that doesn't enclose the origin, the eigenvalues, or the roots of this polynomial, will trace out a braid that looks like this. And it doesn't really braid because the winding number about the hole is 0. If I do a loop like this blue one here, and I ask what the eigenvalues do, they twist around each other once. So this is the n equals 2 case, and this is what I'm claiming is, yeah, there's some topology here, but it's not that exciting. We've all heard about winding numbers. Okay, so this is the summary up here. For an n equals 2 system, you have a plane to move around in, you have a single point of degeneracy. We already knew that your fundamental group was going to be the braid group over 2 strands, so B2, and here's a little drawing of it. What happens when we step over that green line, when we go into the land that I said would be more interesting? So we have a 3-mode system. Here's the most general characteristic polynomial for a traceless 3x3 matrix. There are 2 complex numbers, x and y. Once you tell me your masses and springs, et cetera, you fix x and y. So if you want to think about the space of all such things, it's a 4-dimensional space, which I've drawn as best I can here. Forgive me a little bit, but this is supposed to be 4-dimensional Euclidean space. And now I want to know where in this space do the degeneracies live? It's, again, sort of easy to see that the only 3-fold degeneracy is if both x and y are 0. If that's the case, you have 3 roots, so that triple degeneracy lives here where all the coefficients are 0. But that leaves the question of where are the twofold degeneracies? We need a two-dimensional surface of degeneracies, right? Because we have a four-dimensional space. So where are they? Here's something that I learned in the course of doing this. If you want to know whether your polynomial has a degeneracy or not, there's a very straightforward relationship that its coefficients have to satisfy called the polynomial discriminant. For a third-order polynomial, if the coefficients y and x stand in this relationship to each other, you have a double root, maybe even a triple root. Okay, there's a nice article about this on Wikipedia. And, so where then do x and y stand in this relationship in this space here? The answer is so cool, I'm actually going to walk you through 2 or 3 lines of algebra, and it's going to be worth it, I promise. Okay? So in order to do that, let me replace these kind of Cartesian coordinates for these two complex numbers with their polar expressions, r e to the I theta and rho e to the I phi. And just as a temporary crutch, we're going to remove this later, let me fix myself to work on the surface of a hypersphere, a 3-dimensional sphere, which means that those magnitudes squared add up to something. I'm not going to assume that it's small or big or 1 or anything, just a sphere of some radius. You can see pretty directly that this relationship and this relationship give me 2 equations for r and rho. And so I can solve for r and rho. I know what they are. They're not particularly interesting, but they are some number. And it leaves me still uncertain, though, what this theta should be and what this phi should be for me to satisfy this constraint of degeneracy. Well, if you have 2 unknown angles that both run from 0 to 2 pi, Physics 261 students, what is that? It's a torus. So wherever the degeneracies are on this sphere, they lie on the surface of a torus. Okay. So which points on the torus satisfy this relationship? Well, I need that this squared equals this cubed, which is the same thing as saying that twice one phase angle has to equal 3 times the other phase angle. That's just these points here shown in green. It's the points where a line where if you go around twice the big way, you go around 3 times the little way. This curve has a name. It's called the 3-2 torus knot, or more colloquially, the trefoil knot. So this is the cool thing that I was going to tell you about. Once I peel it off this torus, which is just there to help me calculate, it looks like this. So just these few lines of algebra tell you that the twofold degeneracies on this hypersphere form a trefoil knot. Now I get to fill in the rest because there's nothing special about the radius of this sphere. On a smaller sphere, I'd have a smaller trefoil knot. All the same math would apply. And on a smaller sphere, I'd have a smaller trefoil knot, and out further, I'd have a bigger trefoil knot. And so all the degeneracies are some kind of 2-dimensional surface. It's very hard for me to draw, but like each slice of it would be a trefoil knot that extrude down to a point, which is the 3-fold degeneracy. So that's what this little bit of algebra has given us. And so there are physical consequences of this, maybe unlike the Abel-Ruffini theorem or whatever. If I go and build a 3-mode system and tune its spring constants and this and that and raster through that space, the twofold degeneracies will lie on a trefoil knot. And furthermore, if I pick a specific system with its parameters fixed and then vary those parameters in a loop like this, I will get a braid of eigenvalues that is different depending on whether the loop looks like this or it looks like this, encircling the knot in this way, or encircling the knot in some other way. And at least intuitively, you can see that the question of do I encircle a point in a plane is much less rich than how many different ways in 3-dimensional space can I wind through a knot. So that's where the interest is going to lie. Okay, so this is the answer now for 3 oscillators. You have a 4-dimensional space. The degeneracies are, it's called a cone of the trefoil knot. And here's, again, my best attempt to kind of try to draw this. It's a sheet where every slice is a trefoil knot. We could keep going, but I promise not to for 2 reasons. 3 reasons. 1, I don't know what anything else looks like. 2, you probably don't want to hear any more about this. And 3, all the key features in higher orders are already apparent here. In general, the degeneracies for these higher orders will be some kind of knot-like structure. The space around the degeneracies will have as its fundamental group the non-abelian group of the braid group over n elements. And when you go around a loop, your eigenvalues will form a braid determined by how the control loop winds around this knot. So I should tell you, I did not invent this. Nick did not invent this. This math has been understood at least since the 1920s. And so as an experimentalist, there's no need for me to go out and verify it. Like, is it right or isn't it? It's just math. It's true statements. But I would say that if a system as ubiquitous as the coupled linear oscillators has some elegant mathematical structure that hasn't really been appreciated much to date, it's worth going out and measuring it and seeing it at least once. So that's what I'll tell you about for the next little bit. But before we move on, questions about the basic goal. So I'm going to try and do an experiment where we measure this knot and show that different loops through it give you different braids of eigenvalues. Yeah.
Where is this non-Hermitian aspect coming in? Because all you've said is basically requires a generous. So
I'm talking about systems. Yes, absolutely. So what I'm talking about is a oscillator system where you can tune all the linear couplings. And like linear couplings that involve momentum will look like damping. So if you, so I guess what I would say is, if you want to talk about Hermitian systems and in exactly the same language, this would be the language of the spin 1/2 quantum mechanical system. And the spin 1/2 quantum mechanical system, the space of spectra is one-dimensional. The only thing it cares about is the magnitude of the magnetic field, and there's a degeneracy at the origin. And you can tell equivalent stories, but in Hermitian systems, the degeneracies are 3 dimensions less than the full dimension. So there's no notion of going around. They have plenty of interesting properties, but it would not be this.
One small comment.
Yeah.
At the beginning, you said to apply this also to the Limblad equation. However, that is not a simple equation because it's not for a vector. And the Liouville operator is a super operator. So we have generalized this to apply to that case. I mean, the density is not a vector.
It is a vector of n squared elements. So you can regard it as a vector of n squared, and you can regard the Liouvillean as
vectorize it.
Yep. So it's not usually the way it's written down, but it is the same essential mathematical apparatus. Okay, so I'm not going to tell you anything more. Instead, we're going to do some experiments. So where can I find this? Like, where should I look for an experimental system that would exhibit this? The answer is everywhere, okay? Anything that has 3 vibrational modes. So it could be this 3-stringed bass guitar, mostly have 4 strings, but I found a picture of one with 3. These could be your 3 oscillators. And here are tuning pegs. That's what you want. You want to be able to tune them and find out how their frequencies change. It could be a continuous object that has in principle an infinite number of modes, but where you just pick out 3 to focus on. Maybe you can glue little lumps of things to this glass and tune these resonance frequencies however you want. Or you could take the spherical cow approach and build something that looks like this, just 3 very clear oscillators, 3 very clear couplings. There is dissipation here, even though I haven't shown it to you, because it's real and everything has dissipation, so you can't get away from it. And the claim that I'm making is that if in any such system you can tune 4 parameters and measure the resonance frequencies as a function of those 4 parameters. So these are the 4 things that determine the characteristic polynomial's coefficients. And if you can move around in that space and measure the resonance frequencies, you'll find that they do whatever. But if you ask where are their degeneracies, they will lie on this sort of sheet of trefoil knots. Okay, so in our experiments, it turns out that purely for experimental convenience and nothing else, it's nice for us to use a little square sheet of glass and use 3 of its normal modes. So it's sort of like this story here. These are just the 3 lowest drumhead modes of this clamped sheet of glass. Why? Sort of doesn't matter. Again, my claim is it really doesn't matter. You can do this with any system of 3 modes. This is just what was lying around the lab. So in addition to lying around the lab, it has some very nice properties in that you can really tune all of those linear couplings. You can tune the stiffnesses, you can tune the dissipations, you can tune the couplings, you can tune the equivalent of the Coriolis force by placing that object inside of a high-finesse optical cavity and filling it with laser light. And it just turns out that the radiation pressure exerted on this sheet of glass gives you those 4 parameters to tune it in the form of those 3 laser beams powers and the detuning of all 3 lasers. You just detune them together. Just turns out that these are 4 parameters that do what we want. In reality, the experiment is hard. Thank you, Chitresh. Thank you, Yogesh. And there are lots of details, and in reality, it looks like this. But you know, at the end, it's 8504 playing the 3-string bass. Okay, so the experiment works the following. As I said, once you fill this cavity with laser light, you have changed these three modes. You've stiffened them, you've softened them, you've changed their damping or whatever. And so what we do is we set some laser beams that go into this cavity, and we measure these resonances. We just drive the thing as a function of frequency and sweep out the resonance, and we see something that looks like this. And in the parametric plot, it looks like this. And we just fit it to what you would calculate in physics 410 for 3 damped-driven harmonic oscillators. And the fits are really good, so good that we can faithfully back out the 3 complex eigenvalues, where the real part of each eigenvalue is sort of the center of these peaks, and the imaginary part is their width. So a spectrum like this gives us 3 points in the complex plane. What I want to convince you is that we're going to find the point of threefold degeneracy, that our actual control parameters span this 4-dimensional space. And so to do that, I'm going to show you data taken first on one plane through this 4-dimensional space, and then another one, and then another one, and then the other one, which I can't really draw here. I only have 3 dimensions. And what I'm going to do is I'm going to measure spectra at every point in this plane. And at each point, I'm going to take that spectrum and convert it down to just the perimeter of the triangle in the complex plane, because that's something that vanishes only when all 3 eigenvalues are equal. So when we raster around in this plane, we do see that it gets small in some sort of region here. And when I stitch these 3 planes together faithfully like this, and show you all the other combinations you can get for planes in 4 dimensions, it's clear that there's a bright spot in the center, which would be our threefold degeneracy. We can't convince ourselves that we ever get exactly there, but that's fine. We don't need to measure it. What I now want to measure is on a surface that surrounds it, where are the twofold degeneracies? And my claim is that they'll form a trefoil knot. Okay. So let's talk about this surface around the threefold degeneracy. It's a hypersurface, so it is itself a 3-dimensional thing. And for simplicity, we use a hypercube, so the 4-dimensional equivalent of a cube, which is shown more or less faithfully here, as best as I can show it in rotating view. As an object, it consists of 8 cubes, 8 3-dimensional cubes, which are arranged in such a way as to enclose a volume in 4-dimensional space that I cannot picture. But I have heard analogous stories. If I have to explain the surface of a box to my 2-dimensional friends, I tell them, look, it's 6 squares that somehow enclose some space. And they're like, what? That can't be. So I say, yeah, look, you just unfold it, you lay these 6 squares. And they say, of course, I can picture this, but it's not enclosing anything. And I say, yeah, but actually this line touches that line, and this gray one touches all of them, and they're all still squares. And so my 2-dimensional friend is like, okay, if you distort it like this, then I can kind of see what you're talking about. Okay, this is a stereographic projection of the box. And there's an equivalent 1 dimension up. You can take the 8 cubes that actually somehow in 4 dimensions get stick together to form a surface. And there's a nice way to stretch them out by taking the center cube, putting it in here, taking the 6 cubes that touch it obviously, and those are these 6 not quite cubical trapezoidy things on the faces of the cube. And then this last cube gets wrapped around and stretched out to infinity, just like the so that's a stereographic projection, the surface of a hypercube. And it's nice because what we're going to do is we're actually going to take data in literal 3D cubes where we just raster in the most intuitive way our 3 experimental parameters, maybe 2 powers in the detuning or all 3 powers or whatever. And so this lets me do a stereographic projection where I can still pretty faithfully show you the actual axes and actual experimental units. So the way this works is in a video put together by one of the students. These are the cubes in which we take data, and they're all spanned by different combinations of our experimental parameters, but they're chosen such that some of the faces are identical, like this red face and that red face. So having taken data through all of these cubes, we imagine sticking them all together and then stretching them out into this essentially linear mapping of each of the cubes until all the data that lives in those 8 cubes lives either in the center one, these 6 things, or the space around. And this allows us to, again, to really put sensible units. Okay. So here is that sort of hypercube that we went through. It's convenient for us to sort of take data on 2-dimensional sheets. And so these are all the 2-dimensional sheets on which we measured spectra. At the end, we measured about 30,000 of them. The way it looks is the following. Here's one of the sheets, just shown in 2D. Here we're rastering 2 of the powers. And what I'm showing you here is something called the discriminant, which goes to 0 when there's a degeneracy. And it's a complex number, so it also has a phase wrapping. And So this is the actual magnitude going to 0. This is the complex phase as determined from the eigenvalues. We fit all these spectra, get the eigenvalues. That gives us the discriminant. We do it in order to not fool ourselves. We apply image recognition algorithms. So first we smooth the data just a little bit and then turn loose a minimum finding algorithm and a vortex finding algorithm. It says, hey, you had a twofold degeneracy here. And we have a nice microscopic model of the actual mechanical system in the optical cavity, and here's what it would predict. So it all seems to hang together pretty nicely as an experiment. And so having measured 30,000 spectra like this on all these points over here, we throw away all the ones except for the ones that get labeled as a twofold degeneracy. And this is what remains from this 30,000 spectra. So these are the locations of all these things. And if you look at this and you think, you know, you have a bridge to sell me? I say, okay, I'm sympathetic, but once you rotate it, you can really see what's going on. And let me also mention that this color is not some fiction or guide to the eye. Every twofold degeneracy has one more thing to characterize it, which is an angle that runs from 0 to 2 pi. So if it looks like this red part is passing very close to this blue part, it's very easy for us to tell them apart because they have this different color. So that really is a trefoil knot. This is a more conventional dimensionless stereographic projection with no corners or anything. And the solid line there is what we calculate from the microscope. Thank you. Okay, so this is the first thing that I promised you, which is that the twofold degeneracies would form a trefoil knot. And here, the yellow are those data points. The orange curve is fit to the microscopic model. But now I want to show you that this isn't just a pretty picture. This knot actually has really important consequences for how the spectrum of eigenvalues varies. And it turns out that in order to show you that, I don't have to do any more measurements, basically because back here I have this 30,000 spectra. So here what I'm going to do is I'm just going to draw a point in software and then pick out by software all the spectra that I measured that lie on this green loop. And then I'm going to plot those for you. So each sheet here is the complex plane, so 3 eigenvalues at the start of the loop. And then all these points are what the eigenvalues do as I look at the 21 different spectra that happen to live on this loop. And you can see they make a braid, it's the boring braid, which is okay because this is the boring loop. It doesn't encircle the knot in any meaningful way. And again, here's what the microscopic theory. If I do the same thing for a loop like this red one that clearly encloses one arm of the knot and trace out just what the eigenvalues did in all the 61 measurements on this loop, you see that indeed they trace out a braid. And I don't have the rotating version, but these don't come anywhere near each other. They're really winding around. If I draw another loop that wraps through the knot in a more complicated way, the way you can through a knot, we get a different braid. And these are very robust features of the data. Like there's no cherry picking here. Like if you draw a crazy loop like this one, this is the braid you get. If you draw an even crazier loop, you get this braid. If you draw a super crazy loop, you get this one. They're all where the topology of each braid is really determined by the topology of how this loop encloses the knot.
The knot that you have experimentally with your powers, they're continuously related to the parameters of the metrics, right? So maybe the other way around, the parameters of the metrics continuously depend on it. What do you know?
We spent a lot of time measuring this, and we also have the microscopic Hamiltonian, so that we really believe in because those fits are so nice. So you can either calculate it straight from the microscopic Hamiltonian, or you can measure it. And we checked things like that the Jacobian matrix of these 4 parameters is really non-degenerate when you look at how they change that, how they appear as the characteristic polynomial.
Well, the thing depends on whether you get continuously variable.
Oh yeah, right. So that's a good point, technical point. So strictly, the story about eigenvalues says that eigenvalues will vary smoothly for a smooth path through parameter space. Okay. And since what we have are not literally the coefficients, but just some experimental knobs, yes, there's a smooth map between the experimental knobs to the coefficients and hence to the eigenvalues.
Sorry if you said it, but my brain had a little hiccup, I think. So what are the experimental knobs that you're using?
We shine 3 laser beams into this cavity, and there's nothing magic about this, but it's just handy. So you have 3 powers and 3 frequencies. And it turns out to work pretty nicely if you take the 3 powers as 3 of your knobs and sort of just 1 frequency that's moving them all together. Now you could do the three frequencies separately and an overall power or something, but it turns out they all work at least reasonably nicely to span the space of characteristic polynomial coefficients. And then we tune, so we set them, we pick 3 powers into detuning, and then we buzz this little mechanical device at different frequencies and measure its resonance. Then we fit that and we get out 3 eigenvalues, and we ask were 2 of them right on top of each other.
As you mentioned before, like this knot is rejection of the higher order, like the cone of the triplet knots.
Yeah.
How do you know when you make a winding and you're not starting to intersect neighboring knots?
It's very robust. So I proved for you that for a spherical slice, you would get a trefoil knot, but it's very robust. If I take sort of any, like this is sort of where the real knowledgeable people could come in, but like if I take any kind of even reasonable slice through there, I will still end up with a knot. In kind of worst case scenario, I'd end up with 2 knots or a knot and a sort of.
Yeah, that's what I mean. Like, how do you know you're not like running?
A lot of careful experimentation. Okay, so that's the main thing that I was going to tell you. The last thing that I want to show you is about the non-commutativity of this space. So the fact that if you draw 2 loops in the space that is 3 dimensions minus the knot, those loops do not commute with each other. So again, here's our data. These are all the degeneracies. The orange is where we think the twofold degeneracies are. We pick a starting point, which it looks like it's on the knot, but it's not, it's far away. And we consider 2 loops, the red one that wraps around the knot in one way, and the blue loop, which wraps around the knot in another way. And again, exercise for the student to show that this blue guy cannot get smoothly deformed into the red guy. They really are. And again, we have measured the eigenvalue spectra on lots of points around this loop. So here are the eigenvalue spectra as you march along the red. They do this. And then as you march along the blue loop afterwards, they do this. So this is the braid that you would get by concatenating, this is a typo, red loop and then blue loop. But if you do it the other way, this is literally the exact same data. I've just taken the blue stuff and put it on the bottom, and the red stuff and put it on the top. You get a totally different braid. And you can see that just by noting that here, the middle eigenvalue, so to speak, ends up as the left one. And here, it ends up as the right one. So this is loop A, and then loop B is very different than loop B and loop B. Okay, so that's really kind of the end of my talk. This is everything I wanted to tell you. As a quick conclusion, there's a sort of nice thing, which is that a bit of well-known math that is even kind of fun to learn about, curiosity about the form of solutions to polynomial equations has a nice direct one-to-one correspondence to the behavior of coupled oscillator systems. And in particular, I mean, we already knew about this correspondence, but the unusual thing is that there is this dramatic transition between 2nd order and 3rd order, where on the other side of this, there's this interesting topological structure of degeneracies that form knotted surfaces and eigenvalues that trace out non-commuting braids. And this has real experimental consequences that you can measure. As long as you have more than 3 modes, you will see structures like this. And that's what we actually did in the experiment. So let me say a tiny bit about next steps and where things are going now. If you remember way back on some slide, I said that non-Hermitian things are confusing or surprising your first time, partially just because the matrices do different things. And that's everything that I talked about here. I just asked, what do the eigenvalues of a matrix do as I smoothly change that matrix? And they do all this fun stuff. We did not talk at all about this equation. Like, what kind of time evolution actually occurs if your system has a structure like this? Is there something interesting that you can do? And so what we're working on now is measuring, sort of, if you imagine actually in real time, preparing the system in one of its eigenmodes, and then varying the parameters around some kind of loop in real time while that eigenmode is ringing, and then bringing it back to itself. Is there anything interesting that happens that reflects this structure? And we're still learning more about this, but in collaboration with Nick and Judith, we had some interesting predictions about what happens when you move around, like literally within the knot. There's some interesting things that happen. And when you completely avoid the knot, it turns out that the berry phase becomes a complex number, which opens the possibility of getting gain out of the berry phase. So that's something that we're working on now, and these are the folks who are leading experiments in these areas. Okay, so let me just conclude here and thank the folks who worked on the experiment that I told you about, our funding sources, and thank you very much for your attention. Wonderful talk, and we have time for questions. Yeah, sure. The people on Zoom, the mic is.
So when you drew your hypersphere and you drew the polynomial discriminant and you talked about polar coordinates, you showed us that there's a trefoil knot. And I think you said that in higher dimensions, we didn't expect anything different. Is that true?
I don't know of any. I bet there's stuff that's different.
Okay.
I don't know of anything that's different. And no one, yeah, anyway. But the things that are the same are these. So there might be additional new things that are interesting, but all these statements will still hold true that they do for n equals 3. The surface of degeneracies is some kind of knotted structure. And yeah.
Would there be a knotted structure? And this is my actual question on like a genus 2 torus instead of 1?
It's not that simple.
It's not that simple.
I've asked knowledgeable people if there's some very simple extension of the story, and the answer seems to be no. It's not easy to visualize. So.
Yeah, thanks. It was a great talk. So one thing I can imagine is while it's very difficult to visualize this, it would be almost trivial to hear it. Do you know if maybe what you're observing has maybe already been exploited in, say, the design of musical instruments?
So I've talked to some composers about this, and specifically, not exactly this, but more about Berry phase. So there are some composers that make use of phase, like the actual phase of the sound wave, but not very many. And it would be very interesting, like if there was something where, like, you know, two instruments are playing the same note, so to speak, but yeah, they'd be tuning pegs that would change the eigenmode while keeping the eigenfrequencies fixed or something like that in the extraction sort of phase. The person seemed moderately interested. But to come to your question, like violin designers and piano designers, there are folks who do that quantitatively and do real finite element stuff. And they are interested in degeneracies. And they're interested, like, a parameter will be like the stiffness of the violin neck. And as a function of that, like, normal modes will avoid each other. But I've always seen the discussion in terms of just the real part of the eigenvalues and the usual story of avoided crossings. I've never seen them looking in the complex plane about what's really going on.
Okay, cool.
I'm thinking about the line widths of the sort of the three modes that you need to kind of jointly fit and decompose into the three constituents. I guess naturally, since you're dancing around degenerate points, you're going to be in this regime where the frequency difference between your three modes is very small compared to your line width. No.
We're not interested. Okay, partially, yes. Actually, yes, you're right. Not ever particularly interested in getting close to that threefold degeneracy. We want to know it's there, and so that we're enclosing it when we take our data. But yeah, when we get to the twofold degeneracies and we want to find this, yeah, there will be two that are sitting essentially on top of each other and one that isn't.
When you're actually touching the trefoil, that'll happen, but maybe you can maximally avoid that while still doing interesting braiding stuff when you're passing right through the center of it, maybe?
Braiding stuff, you don't have to get anywhere near the knot. This is why it's topological. Like if you want a winding number for a plane in a hole, you don't have to go anywhere near that hole.
You don't need to go near the trefoil.
If the knot is big, I mean, in some sense, you'll have to go through it. But you know what close is, I'm not sure what that means. You don't have to, like, yeah.
I think that's what I mean though, is if you're wanting to wind around it, but only part of it, you kind of need to go through the structure to some degree. And maybe you get the best resolution, the best separation between your modes by passing right through the center of it, perhaps.
To draw it, so this is sort of roomier than it looks.
Okay.
So this red loop really stays from the point of view of our ability to control things, for things to be stable and well behaved. This red path is quite far from the knot. And you can sort of see that in the, again, if I had a rotating version, you could really see it. But these eigenvalues never get particularly close to each other. Again, with respect to kind of the scatter and noise and our ability to resolve it.
What's the typical like number of line widths that your modes will be apart from each other? How easy is it to resolve them?
So it's not, again, it's you don't need to be more than a line width. Your fit needs to be really good. So here, in fact, you're not a lot of line widths away. This is your line width, and this is frequency. So they're sort of order each other. And you can more or less see that in the raw mechanical spectra, like right here. Right? So if I just showed you this, you might say, oh, you're not resolving the peaks. You don't really know what the eigenvalues are. But no, this data is so, like, there's noise on here, but you can't see it. Like, this system is extremely well behaved, extremely stable. So when we fit like these three curves, like these fits capture every little funny bump and wiggle in the complex plane. And so we don't need to resolve the peaks.
Okay. Yeah, I'm just thinking about line width and memory span of the system and dynamic pictures, but I guess that's the next paper.
Well, there's no reason why to have this knot, you would need this. Like there could certainly, if you're designing this from scratch, you could definitely come up with a situation where the knot was big enough so that when you went around it, your line widths were always smaller than your frequency space.
They're
comparable.
Thank you.
Thank you for the very interesting talk. Are there any interesting symmetries you observe in the experiment if, say, you were directly on top of the knot or traverse the knot?
We haven't explored that much. We don't have a natural way to sit right on, like that's a set of measure zero. Like in some sense, we never can do what you're asking. But you know, we can get very close. And yeah, there are some interesting things. So you're asking about like the resonance line shape, when those two things really sit on top of each other. You know, it's sort of not a Lorentzian anymore. It can have some interesting properties as filters. The time response is different. But that's not something we've really explored.
Okay, thank you.
So in the last slide about the future, you were talking about the time dependence. What are you planning to do that? Because in the case of the eigenvalues of the Liouville operator, this time dependence is very important because the real part of the eigenvalues is related to the decay time, and so it would be extremely important if you could tell us something a little bit, because we've been trying to understand the degeneracies of the eigenvalues of the Liouville operator.
Yeah, I would love to hear about this. I showed the Lindblad equation without knowing anything really about it. But I think, you know, we can do a certain amount of simulation. I'd be surprised if there's anything we could do in our experiment that would be easier than just doing it computationally. But if you have ideas about interesting things to look at.
Maybe we should talk about that.
Thank you for the very interesting talk. How are the conclusions you made in this talk robust regard to perturbations? So I'm asking this because I want to know whether this just provides a way of classify a chaotic system, or you are looking for some like topologically protected phase.
So there's no chaos here. This is just linear oscillators. There's no chaos. This structure, like the sort of knotty structure, it's very robust. So if you have a three-mode system, you have four linearly independent control knobs, you vary them around on a surface, you will see this knot. Not some special, it's always there. This is a totally generic property. Unless you pick a super weird surface, but like, it's a generic feature. In terms of topologically protected phases, you know, there is some, I'm not sure exactly what you mean by that, but there is some interesting stuff in what I would call the Berry phase or the geometric phase of the time evolution, which is where you prepare a state and then you slowly change the Hamiltonian, so to speak. You slowly change the dynamical matrix in a loop, and you ask, what phase did my oscillators accumulate? And there's this sort of dynamical phase, the trivial phase that you just get by integrating up the eigenvalues. Then there's the next order correction, which is the geometric or Berry phase. And it has some interesting properties in non-Hermitian systems that we're still working to understand.
Maybe a follow-up. So would any of this result apply to studying the dynamics of a system, or this is just like the eigenvalues?
What I showed you is just the static spectroscopy. And so we're trying to understand, like there is such cool stuff in the static spectra. Does it manifest itself in the dynamics? We think that there are some ways in which it does, but we're still feeling our way forwards. If you want an example, you can look at this paper here.
Okay, thank you.
Well, let me point out the obvious. If you have more questions, Jack's office is on the first floor of his building. Let's thank him again for a wonderful talk.